So let's talk about energy dispersive spectroscopy. That's what we shortly called as EDS. So we try to cover this material characterization map from our initial slide. So we try to cover each and everything like SEM, TEM, and those EDS things. Now EDS, what we are referring, it's also related to SEM and it's also related to TEM. So first we try to cover the basics of EDS, how we are getting such results and why we are getting such results. Then we will see, if possible, we try to differentiate EDS of SEM and TM later on, if time permits. So if you remember the electron matter interactions, when the electron is coming as like a primary source, then there are possibility for the secondary electron from this electron energy. The electron from the K shell is inner shell is getting detached, and this is a secondary electron emission. And there are possibility for backscattered electron without any interaction with electrons over the initials. At some point, when the electron is detached from the inner shell, to balance the energy, the electron from the like external shell or the outer shell try to come into the inner shell. And again, to balance the energy, there is a possibility for take a laser point. Yeah, there's a possibility for X-ray to be emitted. This energy difference is now energy packet is like an X-ray, and there are possibility for Auger electrons in addition to these things to balance the energy. There is another electron may possibly come out from the outer shell. Those are the Auger electron spectroscopy. Used in Auger electron spectroscopy, or this is also called as X-ray emission or X-ray fluorescence, as it is related to the light. So X-ray is a photon of electromagnetic energy. So the concepts of rest, mass, and momentum embodied in electron energy are irrelevant, and X-ray has no mass. And X-rays, like all electromagnetic radiations, travel at the speed of light in a vacuum, and consequently we don't have to make increasing realistic corrections as their energy increases. However, we can also have some quantum calculation like E equal to h mu and hc by lambda. So the wavelength of this can be calculated with respect to the energy, 1.24 divided by E in kilo keV. Right. So this is just like a basic slide for X-ray. What are the characteristics of those X-rays? A high energy beam electron must penetrate through the outer conduction valence bands and interact with inner shell electrons or the core shell electrons. If more than critical amount of energy is transferred to an inner shell electron, that electron is ejected. That is, it escapes the attractive field of the nucleus, leaving the hole in the inner shell. In an isolated atom, the electron is ejected into vacuum, while in a solid, it escapes above the Fermi level into the unfilled states. The atom is then left in an excited state because it has more energy than it would like, and we describe it as an ionized. Right? So those ionized atom can return almost to its lowest energy by filling in the hole with an electron from the outer shell. Right. So this transition is accompanied by the emission of either an X-ray or an Auger electron. In both cases, the energy of emission is characteristic of difference in energy between the two electron shells involved, and this energy difference is unique to the atom. So as this is unique to each and every atom, so with the energy calculations, it's easy to identify what type of atom it is, or what type of atom emitting such X-ray with such energy. So that's the calculation behind it. So the ionization process can occur as a result of X-ray bombardment also, in which case we use the term fluorescence. If you remember the first material characterization talk, I was talking about even X-ray fluorescence spectroscopy. So as like electron is bombarding into the material and getting X-ray through the process which is described here, there is also possibility for X-ray bombardment and getting such X-ray through such process of such energy filling process and energy balance process as described as similar to electron. So that's why we call this X-ray fluorescence. So there are maybe in your bachelor's or the basic chemistry study, you might have come across the ionization energy of a material. So ionization energy is the energy which required to make ionization of that particular atom, right? So it varies with atom by atom. So now we need to know what is X-ray energy. What's the difference between that? If you read here, sorry. A copper K-shell electron requires 8.993 keV of energy for ionization. That's AC is 8.993 keV. One possible sequence by which this extra energy within the atom is lost is the first by creation of copper K alpha X-ray. Right. So the first K-shell electron has to be replaced and detached. Then from the L to K, there is an electronic transition. The X-ray is emitted. So for that, it requires 8.048 keV. That's the X-ray energy. Right? These X-ray energies in total, then L X-ray energy is 0.930. That's from the L shell now. So one is from the K shell, another is from the L shell. In total, it makes an X-ray energies of 8.978 keV, and the remaining few electron volts when compared to the ionization critical energy, that is 8.993. Now we got X-ray energy from the K shell, it's 8.048, and from the L shell, it's 0.93. So there are remaining few EV, right? So those few EV could come from the hole in M shell being filled from the conduction band with the emission of photon or the generation of phonons. So this is what happening. This is what we try to understand. When electron or X-ray is bombarding the sample, there are possibility for the X-ray electron to go to the higher energy state, and again it comes to the ground state. There are possibility for K shell and L shell rearrangement from the whole creation and the electron replacement from one shell to another shell, and making the emission of photon or generation of phonons to balance the energies or replace the energies. So this is what happening in perspective of energy scales. All right, now we have a sample. We have X-rays are emitted. So there are some EDS detectors, and this is an angle like from the surface of the sample to the detector. This is called takeoff angle. So this angle can be like increased or decreased with the tilting of the sample. It is required in TM in particular. It's making tilted towards the detector, but at the same time, you need to keep in mind the electron should come and hit the sample. Then only the X-ray will be emitted. So you need to balance those tilting angle to get as much as possible electron to the specific region and towards the electron EDS detector. But in ACM, mostly we are not using any much tilting. Of course, we need to tilt when it is required. But in most of the ACM cases, we try to just take without tilting. So once X-ray is coming from here to the detector, so these are the possible things happen. The detector gets this X-rays. Then there are possible signal processing. Then goes to it makes an X-ray spectrum through the energy calculations, because all this energy is related to the atomic shell arrangements and how these electrons are getting into such shells, transition within the shells. So this emission of characteristic X-rays depends on particular atoms. That's what we need to remember and recall. So such once this X-ray is coming to the detector, for example, there is a beryllium window, or there are anti-reflection coating there to avoid a reflection and get as much as possible X-ray into the detector. So there are mostly a beryllium window, or sometimes there are new channeling window here to get those X-rays directly into the detector. It acts as a channel for the like a transparent channel to make X-rays to travel towards the detector. And then there are within the detector, there are two types of possibles, like silicon or lithium based crystals. So here, for example, when calcium K alpha rays is coming in, there are possibility for interaction with the silicon atoms here. And again, there are possibility for electron hole separation. And such separation, then electron hole pair recombination will be calculated in later stage. So that's how it identify, okay, such type of K alpha is coming from, like with such energy, it must be coming from calcium, or if you are getting more KeV, then it must be coming from copper or some other things. That's why we try to identify such energy by the reaction or the interaction with silicon window or silicon crystal within the detector. So there are, as I told you, with beryllium window, there are new types of windows, which is boron nitride or diamond or polymer, which is of 0.1 nanometer to 7 nanometer nowadays available here. It acts as a channel and get all the X-rays into the detector. Then when it comes to the detector, a positive bias attracts the electrons to the rear ohmic contact, and this charge pulse is amplified by the FET. So there is an electron trap. It can be if there are some electron escapes from the sample surface, and when it possibly travels together with X-rays, the electron trap is placed here to get those electron trapped trapped before the X-rays is going to the crystal, and the reactions of interaction is possible here. The generation of electron hole pair occur. Then the FET, it amplify the process, the whole process later on. So this is what happening from the detector side. The new type of detector is a solid, like a drift detector, which have nanoscale silicon material like this. There are more windows, there are more possibility for more perfect reactions in modern TM or in modern SEM EDS detector. Whatever the detector, whether it is silicon crystal or the SDD detector, the detector consists of a collimator. It acts as like an aperture. The collimator is nothing but is an aperture. A collimator to ensure that only X-rays generated from where the primary electron beam interacts with the sample will be collected. So it determines the energies. Only the X-ray generated from the primary electron beam interacts with the sample will be collected. It avoids other X-rays. So electron trap to ensure that X-rays, but no electrons enter the detector. A window to isolate the detector crystal under high vacuum from the chamber of the microscope. The older windows were composed of beryllium, which did not allow low energy X-rays like less than 0.9 keV to pass through it, but more modern windows are composed of polymers that will allow low energy X-rays to pass. So that's why in advanced EDS, beryllium window is started to replace with other type of materials. So the semiconductor crystal detector is available. Then the electronics to detect the charge recorded by the detector converted it to the voltage pulse and pass it to the pulse processor. So this is what we need to understand from all these slides, from here to here. So I just try to put all those in lines to make better understand about what's happening in the EDS detector side. So apart from that, the basic operating principle is same for all types of detectors. The energy of incoming X-ray is dissipated by the creation of a series of electron hole pair in the semiconductor crystal, like here it is silicon. A high bias voltage is applied across the region, and then electron holes to move to electrodes on opposite sides of the crystal, producing a charge signal which is passed to the pulse processor. The size of signal is proportional to the energy of incoming X-rays. So for silicon detector, that is 3.8 electron volt is used to generate each electron hole pair. In germanium, it is 0.29, that is 2.9 electron volts. So for an incoming nickel K alpha X-ray energy 7.47 keV, that is 1,968 electron hole pairs will be produced. And for aluminum, it is 391 electron hole pairs will be generated. So now the system will try to understand whether this X-ray is coming from nickel or aluminum based on how many electron hole pairs are generated. So those are the electronic detections later on. So to minimize electronic noise, the detector must be cooled. That's why we use liquid nitrogens always into the dewars to make it as cool as possible. SDD can operate at high temperatures, that is around minus 70 degrees centigrade, and employ thermoelectric cooling, which is significant saving in time and money. So this is the advancement, like it can operate at minus 70. So it's not higher temperature, it means plus or 700. It means compared to the liquid nitrogen minus 273, minus 70 is higher temperature. That's what we need to understand here. So silicon or lithium detector crystals are about 3 millimeter thick. X-rays produced in SEMs may have energies up to 30 keV, and these will be efficiently processed by silicon crystals. Higher energy X-rays, for example, 100 to 400 keV, as produced in TEMs, will pass through the silicon crystal, and its efficiency declines at energies above 25 keV. So the intrinsic germanium detectors maintain their efficiency to process X-rays with energies in excess of 100 keV, which is why they were preferred for some TEM detectors. Like what it is mentioned here is like the differentiation of detector between SEM and TEM. Because of the higher energy from TEM, we need a germanium or intrinsic germanium detector to maintain the efficiency. That's why TEM detector is completely different compared to SEM detector, because in SEM we use only approximately 30 keV, but in TEM we use from 100 to 400 keV. So because of those high energy, the energy of incoming X-rays may get a little varied because of that we need an efficient detector to accommodate all these things. So this is like an TEM EDS detector with silicon lithium detector with beryllium window here, a collimator. Here is the sample, so it's placed here. So sometimes that's why we need to tilt TEM sample at least up to 15 degree tilt, what it is recommended in all the TEMs. To get more closer to the takeoff angle towards EDS detector. But as I told you, you need to remember the electron beam is coming here, so that if you cannot tilt it more than that. If you tilt it more than that, then the electron beam which is coming here in a 90 degree tilt, 90 degree orientation will not have possibility to react with the sample. So the X-rays generation will be reduced. So that's why we need to balance here with some tilting angle to get electron and then X-ray. But in advanced TM, at least what the stem I was using, which have a super X detector, which means there are some detectors in a 4 different angles. So you don't need to tilt the sample. It gets X-rays from all the angles, and these advancements, it's more specific for the chemical quantifications. Yeah, so such advanced X-ray detector is possible, and there are some TEMs which have just two detectors instead of 4, but it's placed as close as possible to maintain the takeoff angle and to get as much possible X-rays without any tilting. So this advancement makes more chemical quantification efficiency possible in nowadays with TEM. So we need to understand how these energies are generated. Now, so far we saw about the detectors. Now we are jumping into the X-ray characteristics more in detail. So there are possibility for the primary electron which comes here. So it hits electron on the K shell. Then this will be placed here. This electron is already jumped from here to here to the from K shell. Then this incoming electron may have some energy loss with the interaction of K shells, right? So that's the energy loss electrons now. So there are possibility for yields, this energy loss spectroscopy, electron energy loss spectroscopy to capture such electrons, that is energy loss electrons. So it now identify each an atom have their own K shell energies. So in that way, when these energy loss electrons are coming, then when it is detected, it's easy to identify the chemical nature of the particular sample by using such monitoring. So that's how whether you can use X-ray or you can also use yields to identify the chemical nature. So, but before going into X-ray analysis or EDS analysis, you should remember this periodic table with X-ray energies, because this is more important. For example, you have K shell energy of 6.74 and L energy of 0.75. So, which is for in case of iron, and in case of nickel, this is varying, and in case of cobalt, it has another variations. For example, in case of chromium, it have L alpha energy of 0.572, which is also slightly matching with the K alpha of oxygen, and this fluorine 0.677, it's also slightly matches with Mn and L alpha lines. So sometimes it's easy to get confused with the peaks if you are not understanding this K shell energy and L shell energy periodic table. Then whatever the signals you are getting from EDS mapping, then you just try to understand, okay, this is from Fe, this is from cobalt, as it is just matching with like automatic peak identification techniques through the softwares. It's easy to get confused, because try to remember, whatever the sample you have, whatever you do, you get some X-rays. All those X-rays are related and mapped in your peak regions, like within the peaks. So, for example, this rubidium and platinum have 2.83 and 2.69. It's also sometimes related to chlorine, K alpha, and sulfur. So the system, if you do just automatic identification, it's just say one element instead of another element because of the intensity calculations. But so that's why I said it's easy to get confused through that way. So you need to know these things. You need to play with such peaks, and you need to check what really it contains. So that's why before getting into EDS and before getting into analysis, at least you should have such periodic table in your hand to know to mark the regions and to mark the peaks. I will show you what are the artifacts we may possibly get in later stage anyway. So another thing is, even within the K regions, you have K alpha, K beta lines, and sometimes a K alpha of one element, like a peak, is also matches with K beta of another one. I will show you one example, because we used to get more confusion over that region. Like for example here, just take chromium and manganese. The K beta line of chromium, that's 5.947. It's also like a K alpha of manganese, 5.90. So it's when you have alloys like a metal alloys or any alloys with the composition of chromium and manganese, you have peak there, but you don't know whether it is chromium or manganese. Of course, the recent advanced EDS detector is trying to match those things. I will show a few practical software examples later on if we have time. But in other terms, you need to think over it. You have the peak, but you cannot calculate, or you cannot define that whether it is from manganese. Then if you just do automatic mapping, system will tell some calculation like chromium of 50% and manganese of 30% and other elements of some percentages. Then you will write something. So that will be an error. So first, what we can understand here from K alpha and K beta is, K beta line is always a reduction of 10% comparison to the K alpha. So when have K alpha peak up to 100% of intensity, so the K beta of chromium or any elements must be 10% of reduction. So it means just 10% compared to 110. Or K alpha is 100, K beta is 10. But if you have real manganese peak of K alpha, it should have peak intensity more than that one. But it also have, sometimes it also have K beta of chromium within the packed region. So only the recent advanced system will try to identify those things. Otherwise, whatever the chemical quantification you do with some percentage, it's not actually the real one. Try to remember that we have such interference in all the K alpha, K beta, and L alpha, L beta over this like periodic table of elements. So if you remember, if you see all the data, there are 4.0 here. Again, there are 4.013 with the K beta here, and tellurium's L beta is also 4.02. So most of these low numbers of like, for example, K alpha of like silicon, it's also sometimes matches with platinum, where it is 50, platinum 78. Yeah, there are possibility for M alpha lines, which in our experience, there are more, the platinum signals are matches with silicon, and it's easily get confused. So those things happened, and sometimes we have cerium, which is 59, I think. Yeah, 58. Cerium line of L beta, it's also sometimes matches with other elements, and we get confused with such things. So we sit with the software and we do post processing a lot, taking all these parameters in mind. So it's happening because when the primary X-ray it's hitting or the electron, for example, in our case, electron or X-ray is hitting here, the K shell electron will be jumped out. So the nearest one is a L shell. The electron from L shell comes here to replace here, which means this is a K alpha X-ray emission. And if the electron from M shell is coming here to replace here, so it means this is a K beta line. So that's what we need to understand. All the elements have both possible emissions. So you need to know all these are possible things. Like, for example, a single element have K shell emission, L series emission, and M series emission. And even within the K, for example, there's a K alpha and there's a K beta. If you remember, I told K alpha and K beta is like a it's varied by 10%. So if this is 100, this is 10. So this is 100. This is like that's only for K line. This is something I think if it is related to 50%, if I remember rightly. So all these lines are possible. So this is from K alpha 1 and K alpha 2, and because of the different energy lines within the L, and from here it is K beta 1 and K beta 2, such that every atoms and every lines have their own alpha lines and beta lines and gamma lines. So you need to think over all this before analyzing EDS. So if you see this one, it's like a more complicated from the perspective of some energy arrangements of shells. All the lines have all type of energies. So don't go for automatic peak identification in EDS. And sometimes I used to write in a review, like if someone claims from the SEM EDS that we have such percentage of A element and such percent of B element, I said, just use the peak, just use the peak image. Don't say that what percentage you have, because you cannot finalize such quantifications by using SEM EDS. At least in modern SEM, it's okay. We have some percentage of new algorithms in modern SEM EDS softwares, but in TM it's okay. Some it's more advanced, and it's getting more and more advanced in recent days. As I told you, as I show you a few images, like it have Super X detector nowadays possible. It collects all the greater takeoff angles, and it collects all the X-ray energies, and it process. We can simulate it and take an algorithm which is fed already, and it shows what type of energy is from which one. But not in all the SEMs, not in all the TMs. Try to remember that. So don't claim you have 50% of iron and 50% of chromium in your sample. just because of you have such calculation from EDS. It will be wrong. At least in most of my review cases, I just wrote politely to not to write that, not to mention that. So microscopist knows this very well. And in SEM, you are collecting many signals from specific spot angles. At least in TEM, at least in modern TEM with STEM imaging, you are going scanning by atom, or within few nanometers by few nanometers. So you have more chances for more accuracy. But in SEM, it's the spot size is very bigger in tens of nanometers. So you're collecting many signals within those regions. So with SEM EDS, you cannot claim the quantifications as accurate as possible, and it's always going to be wrong if you're not taking all this into the account. So with X-ray or EDS, we are coming across few terms like a count rate and dead rate. So when the K alpha it's coming here, within the beryllium window, it first filters out, then it processed, right? At some point, when there are more X-rays coming together, sometimes the system will get confused of taking everything together and may bring some results. So you set the system for some percentage of dead time. Like in SEM, we try to set around 30% to 40%. In that sense, we try to give space for the system to filter out incoming radiations. So by that way, you get this to be processed and this to be processed one by one. So of course, in some system they said 20 to 50% dead time is acceptable, but within my experience, I try to work around 30% of dead time. Somehow it's balanced in some space. So with the dead time is a period during which the detector is busy and cannot accept process pulses. So this can introduce error unless it is accounted for, right? So either by extending counting time. So you say the system, like you take account you process the X-ray by some values. So in it means you are setting some lifetime. That's possible in all the EDS softwares. So you set that one and say the system to get as much as possible, or decrease the dead time to say the system, okay, you process first this one, then coming to the next one. Like that, you can just feed some data. By that way, you will get more and more as possible as efficient result. I cannot say it's again 100%. Always remember, whatever the system, whatever the sample, whatever the signals you are getting, you have some mapping or you have some peaks. So just try to remember always whenever you're doing some calculations. So what are the practical consideration? I was talking about dead time already, but this is about TM. But as of now, I'm just leaving these words. This is some calculation related to like a system, how it calculates the dead time. I'm going for the sample perspective now. The specimen must be stable, flat, homogeneous, and void-free, because the X-ray coming from this region is different from the X-ray coming from this region, because this may possibly get absorbed here. So there are possibility for region-wise differentiation. Also, if you have some precipitates here and there within some window of analysis, then again it shows different results. Different elements will be added on later with respect to the regions. And here, for example, here there is an incident beam, the normal flat bulk target absorption path, but here here it is like an extra absorption path due to the ridge over this region, and again reduced absorption path due to the scratch wall. If it is sometimes, if there are some scratches, there are more absorptions possible over those region. And when it is going deep and deep, the extra absorption path also possible in the deeper sections. So it's also varies with region by region within the same material, within the same localization. But try to understand that maybe possibly happen because of such material problem or materials physical nature. Then, okay, for example, as you remember from the periodic table, iron have a K alpha energy of 7.11 keV. So when you use more than 15 keV, then you get a clear identification of this K alpha line. But if you set the system SEM for 5 keV, then you don't get signal here. Then the iron region is blank. It doesn't mean the sample not contain iron, but it means you need to increase accelerating voltage, at least double the one compared to the K alpha. Like to get 7.11, you need to go up to 15 kV. So most of the EDS acquisition, at least it depends on the sample, but try to set from 20 kV to 30 kV. 20 kV is also okay, because most of the elements what we are working now, it has a K alpha within the 10 keV. So try to think over that one. And there are possibility for, like for example, silicon K alpha and rubidium L alpha and tungsten M alpha, which comes under the same region of peak. So these are possibly like need to be channeled out. For example, what we do is we say the software to get only calculate, we get all the signals, but when it is finalizing the results, we try to say the system to get only K alpha lines or K lines of all the samples. In that way, L alpha and M alpha will be omitted here. Instead, you can also pick the elements in the software to say, for silicon, try to take only K alpha, and for rubidium, try to get only K alpha, and for tungsten, try to get only L alpha, because sometimes M is missing here, linked here, interfering here. So we should know which type of L and M line is interfering with which another K or L line of another element. So you need to think over that and say the system to take only such signal to finalize quantifications. So not all of the X-rays that are generated in the sample by primary electron beam are emitted from the sample. This is particularly true in SEM, where X-rays are generated within the interaction volume at depth of many microns. X-rays may be absorbed by other elements in the sample due to the photoelectric effect. If the energy of an X-ray photon is equal to the critical ionization energy of an electron in another element in the sample, then there is a probability that X-ray will be absorbed and photoelectron is produced. So this is also like just like a point to remember theoretically. If there are some X-rays which is coming from some elements, and you have another element within the sample, and this X-ray energy is also equal to the ionization energy of that element, it's like a second element. In that way, this X-ray is used for ionizing that particular second element, and X-ray is totally absorbed there, and only the photoelectron is produced. So these type of photoelectric effect is also possible. So in that way, you need to think what are the ways you can avoid all this, and or at least to understand ionization energy perspective of different elements. If you are taking your sample for EDS analysis, you should know these things. And there are possibility for another artifact, which is some peaks, like we have A element and B element, and there are possibility for A plus A. For example, this is 1.7 keV region, and like 1.7 and 1.7 becomes 3.4 peak here. Sometimes this peak and this peak comes together, or it depends on the sample and the particular localist region's X-ray generation. This peak will be wide out, and only you may get some peaks. So you should not get confused with another element, because there are possibility for A plus A peak to be formed here, or A plus B peak to be formed here, B plus B peak should be possibly formed here. So such piling up is also possible. Remember those things. And another artifact, for example, it looks like one X-ray. The calcium have 3 keV. So these some peaks may also possibly comes like a 7.6 keV. So either some peaks is possible, or the escape peaks. It means from the silicon detector results, the silicon channel may sometimes emit X-rays it's not always, it's happened randomly. So such fluorescence also be thought to be like a silicon peak. So, but try to know that these are from, this possibly from silicon escape peak. So in that sense, this energy of 3.8 can be used to make sometimes to make such fluorescence. So the energy of incoming X-ray is getting lost here. So 3.8 minus 1.7, you may get some peak at 2.1 kV, which is close to zirconium or phosphorus. So if you give automatic identification peak in your software, the software says it's from phosphorus or zirconium. So you write, okay, I have zirconium of such percentage. So it's completely wrong. You need to know if you have zirconium in your sample or not. What are the possible way of getting peak there, even though there is no zirconium there? So you need to know that. For example, we have a TEM grid with copper. So whenever we have copper element in our sample, there are more copper peaks coming also from the TEM grid. So we try to avoid copper or try to say the system about either taking KL for K beta, L lines. Sometimes still it's mismatching with the calculation, the theoretical calculation. Then we say, of course, the system detected copper from TM grid. So we cannot say what real percentage of copper we have in the system. So say it openly, say it honestly, no one will no one will be get like a negative points over that, because everyone knows these are the artifacts possible in EDS. So just try to think over it, think over theoretically, and try to add as much as possible information. And if you don't have possibility for saying the real percentage, say it openly, but say it honestly that why you saying it's because you may get silicon peak. In addition, you may get copper peak from the copper grade. You may get another peak from the carbon from the carbon tape if you are using SEM, and even copper from the copper tape. So there are many possibility of artifacts. So this is like yeah. So such intensity is also, for example, this is silicon carbide, which is mapped in 20 kV. You have more silicon, but when it is mapped at 3 kV, you have carbon peak. So these peaks, like then system thinks this energy is very less compared to silicon. Then it try to avoid, because you're using high energy, and this comes from silicon alone. So it try to like make full of things like there is no carbon in your sample. So you need to try to reduce the total energy here. In that sense, you can get both carbon and silicon. So sometimes what I do is, or what we do is, we also do X-ray mapping or X-ray analysis, EDS analysis up to 10 kV or 15 kV. And when we need to know the low energy elements, we also do another EDS mapping at within 5 kV or 3 kV to accommodate all these possible elements. Because at 20 kV, you see here the carbon is missing. So this is one research paper which I came across. Because they have iron disulfide, they have lead, they have molybdenum. All these lines have some coordinated points within this region, and they got summation spectrum instead of a single iron or lead or molybdenum. So they use some software. This is like a research work separately, in particular towards EDS analysis. They do some mathematical calculation, and they try to identify which is related to iron disulfide, which is related to lead, which is related to molybdenum. So this is like a high-end research. You don't need to do this, because it's completely a research only for EDS mapping. So we don't need to do that, but at least just want to show that these are also possible researches going on from EDS perspective. So there are practical limitations on the lighter elements, in particular towards some EDS. So the light elements are difficult to measure, as valence electrons are involved in characteristic X-ray production chemistry. So for heavy elements more than sodium, the K alpha X-ray is not associated with chemical bonds. In that sense, lighter elements won't give you efficient results if you have more lighter elements. So what I do is, even for the oxidation sample, we try to avoid oxygen peak. As we know, within the oxidation layer, we know from the chemistry perspective, if it is from the iron rich region or from the aluminum rich region or from the alloys, we know where the oxygen sits in. So we just try to get only cations instead of anion oxygen. And we just calculate later on about what are the possible oxide combinations in that region. So we try to avoid such low elements in some points. So this is about the light elements. Like as I told you, the light elements cannot be routinely analyzed by EDS. Particularly hydrogen or helium do not have any characteristic X-rays, and lithium K alpha X-rays are too low energy to be detected by EDS. So we are completely avoid hydrogen, helium, lithium. Beryllium to neon X-rays can be detected, but there are two problems. Firstly, there are low energy X-rays subjected to strong absorption of by the specimen. So most of the X-rays are absorbed there. Secondly, the electrons involved in generating the characteristic X-rays are also the valence electrons involved in the chemical bonding of element. Therefore, the shapes and the position of peaks may change in different components. So it depends on which components it have, or what type of elements it have. So there are many many things to be considered in terms of lighter elements. The carbon is most commonly used coating material for non-conductive samples and cannot be analyzed if the sample is carbon coated. A different coating material must be used if analyzing for carbon. Many minerals contain oxygen bonded with a range of cations. It is common practice to calculate the amount of oxygen in the sample by measuring the percentage of cations and calculating the oxygen by stoichiometry. That's what I was telling from my experience. This generally is more accurate than analyzing for oxygen. So I explained you with my examples, right? We don't take oxygen as a considering point when we do the X-ray mapping or X-ray line scans. We avoid that and take only cationic percentage. We know from the stoichiometric chemistry what type of possible oxides are there. So calculating oxygen by stoichiometry requires knowledge of the valence state of cations to which it is bonded. This information is not available from EDS analysis, so it's available from the chemistry perspective. So you need to add on such chemistry knowledge at some point when it is required, together with EDS knowledge.